వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో MBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది.
2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
MSET, ISET, ESET కోడ్ MVRS. వివరాలకు కాల్ 8464887777.
Good morning, students. In the last class, we have discussed about the filters with only the passive components, that is either resistor or a capacitor. Now we are going to discuss about the filters which uses active component. So here you can see the filters using active component. So first we are going to discuss about the response of active high pass filter. Here high pass filter indicates that we are going to give the input signal directly to the capacitor, and we are going to take output from a resistor, and that output will be provided as an input to the operational amplifier. That is here we have considered op amp as a non-inverting amplifier. That is, we have given the input signal through a high pass RC circuit to non-inverting terminal of op amp, whereas inverting terminal of op amp is used as a feedback. So this circuit we have observed in our third unit, that is a voltage follower circuit. So for this circuit we are giving our input. So what happens, we are going to observe now. So the critical frequency can be obtained, that is resistance is equal to the capacitive reactance. So here resistance in this circuit is R, and the capacitance reactance will be given by XC. So we are going to write R is equal to the reactance of the capacitor XC. Then we can write this XC as 1 by omega C into capacitance value. 1 by omega C into this capacitance value. Then we can elaborate this term as, that means in the place of omega C we are going to write it as 2 pi fc, as we know that omega C is equal to 2 pi fc. So R is equal to 1 by 2 pi fc. So if you bring this fc to the left hand side, and if you bring this R to the right hand side, this R comes into the denominator section, and fc comes into the numerator section. So this is what the equation you are going to obtain, that is fc is equal to 1 by 2 pi rc. So that fc, the frequency, that is critical frequency, is going to depend upon the values of r and c. That is, critical frequency is inversely proportional to r and c, you can observe here. So if we modify the values of r and c, then we can modify the value of fc. So fc can be varied with the help of varying this r and c. So this is how the critical frequency will be obtained for a active high pass filter. So here, as we have observed that the response of high pass filter, which allows only the high frequency signals above the critical frequency. So this is the critical frequency. This high pass filter allows only above the critical frequency, whereas here, coming to the concept, so our main theme is that high pass filter, what happens to this high pass filter? Attenuation rate. This is the attenuation rate, that is here, this we are calling this as a roll off rate also. So if we consider a single high pass network with a single high pass network, that is nothing but a single pole, then the attenuation of this high pass filter will be 20 dB, minus 20 dB per decade. So if we are going to increase number of poles, that means if we use two poles, then the attenuation is going to increase to minus 40 dB per decade. So then here, if we going to increase further the number of poles, that means if number of poles is 3, 60 dB, number of poles is 4, 80 dB, minus 80 dB, 5 minus 100 dB, 6 minus 120 dB, like that. If we increase number of poles, the attenuation rate is also going to be increased. So this is how the attenuation can be increased in filters. So if we consider the practical response of this filter, there in the last circuit we have considered the op amp as a voltage follower. there we have not given any we have not placed any resistors when we are giving the feedback to the inverting input terminal, whereas in this circuit we have given a feedback through a resistor R1 and R2. So here by using this feedback, my op amp is going to act as a active high pass filter. Why? Because here I have used the RC network which acts as a high pass filter, and I am going to provide a feedback through R1 and R2. So what happens to this feedback when I am going to introduce this feedback? So then the gain of, so here I am going to use op-amp as a input is given to, here you can observe that input is given to the non-inverting terminal. Then this op-amp is going to act as a non-inverting amplifier. As we know that the gain of non-inverting amplifier is nothing but 1 plus RF by R1. So there you have, we have observed in our previous chapters, that is the gain is equal to, gain for a non-inverting amplifier is equal to 1 plus the feedback resistance divided by the resistance which is connected to ground. So here the feedback resistance is nothing but R1, and the resistance which is connected to the ground from non-inverting terminal is R2. So for that reason we are going to write this closed loop gain as, that is nothing but a closed loop gain of a non-inverting amplifier as 1 plus R1 by R2. So if we consider this as a non-inverting amplifier, then the frequency here going to depend upon, that is the critical frequency is going to depend upon 1 by 2 pi RC, as we have observed in the last session. In the same way, the critical frequency is going to depend upon this R and C components of this circuit. And then active high pass filter. Here in this slide, we have observed that active high pass filter of a single pole, because here we are going to use only single RC circuit. So here coming to here, here you can see we are going to use a two pole RC circuit in which we are giving input to capacitor CA, and the resistor connected to the feedback, that RA is connected as a feedback, that is positive feedback, and then CB is connected here, then RB is connected to the ground. So here in the same manner, the op amp is going to act as a non-inverting amplifier, and this is called, here we are going to use two poles, hence this is also called a second order high pass filter, second order high pass filter. And this is also named as Shannon key filter. This is also named as Shannon key filter. And when we are going to increase the poles, number of poles, we have observed that the roll off rate is also going to be increased, that is from minus 20 dB to minus 40 dB. So the attenuation is going to be increased, the attenuation of this circuit is going to be increased, whereas here the critical frequency, you can see that a critical frequency FC, which is going to be equal to 1 by 2 pi root of RA into RB. This is Ra into Rb is the resistance of poles which we are adding. So Ra into Rb into Ca into Cb. So if we consider the whole resistance is equal, then we are going to replace it with a R. And also let us consider the whole capacitance, that is the capacitance is equal to a single capacitance value, that is C. Then our critical frequency will be equal to 1 by 2 pi RC, because RA is equal to R and RB is equal to R, CA is equal to C and CB is equal to C. So this 2 becomes R square into C square. So which is nothing but RC whole square. This square and root will be cancelled, and then we are going to get the equation Fc is equal to 1 by 2 pi Rc. Here the critical frequency is going to depend upon the two resistance values as well as two capacitance values. Now we are going to observe the uh, analysis part of this Shalanki or a two-pole high-pass active filter. Two-pole high-pass active filter. Here we are going to consider this circuit. So you can see this circuit, which is you can see this circuit in which Opamp is going to be used as a non-inverting amplifier because here we have given input signal to a non-inverting terminal through two poles RC networks, and then we are going to provide a feedback through R1 and R2. So from this circuit we are going to determine what we are going to determine the transfer function as well as damping factor, and what is the critical frequency and on which factors this critical frequency is going to depend upon. Let us see. So as we know that from virtual ground concept, so uh, if we consider the op amp as an ideal one, then we know that the op amp input terminals does not draw any current. So the current going into this op amp terminals will be zero. That is why here we are going to indicate the current as zero, because when we are considering ideal op amp, this op amp is not going to draw any current. That is why we have written here zero, the current as zero. So here from input side we are going to write the current values. So vi, the current flowing through capacitor C is I1, and at this node it is going to, this I1 is going to divide into two parts, that is I2 and I3. And then what happens, this I3 is going to divide at this node, that is V2. At V2 it is going to be divided into again two parts, that is this part and this part. As this part, as we have considered that op amp does not draw any current, we can say that I3 is equal to I4. Why? Because this op amp is not going to draw any current. So that is why we can say this I3, the same I3 is going to flow through this R also. So now we are going to analyze the response and we are going to find the transfer function of this circuit. So according to the virtual ground concept, as we are considering here op amp as a ideal op amp, the voltages at the inverting terminal as well as non-inverting terminals are equal. That is nothing but the voltage at this node is equal to voltage at this node. So that is what we have written here, that is V2 is equal to Vf. That is V2 is equal to Vf. That is what we have written here, that is V2 is equal to Vf. V2 is equal to Vf. Then after that what happens, so we are going to write the equation for Vf. So Vf is equal to R2. So Vf, from this node point of view we are going to write, so Vf is equal to V naught, that is the voltage at this point, into the opposite resistance of this voltage, that is V naught into R2, which is going to ground, R2 divided by the total resistance in this path, that is R1 plus R2. So Vf is equal to R2 divided by R1 plus R2 into V naught. So as we know that the gain, that is, we know that the gain is nothing but output by input. So here the output is nothing but V naught. In this circuit the output is nothing but V naught and input is nothing but, here, that is input is V2. So this is V2. So output is V naught and input is V2. So the gain is given by V naught by V2. So here you can see this, the gain is given by V naught by V2, which is equal to A naught. So as we have discussed that V naught and V2 is equal at this, uh, as we have considered virtual ground concept, then we can write a V naught in the place of V2 we can write Vf. So as we have determined the Vf value, we are going to substitute Vf value in this equation. So then this equation, when we are going to substitute this equation value, so the equation will becomes r1 plus r2 divided by r2, so which is nothing but 1 plus r1 by r2, so which is going to be equal to 1 plus r1 by r2. So if we observe this thing 1 plus r1 by r2, so then we can say this is nothing but the gain of non-inverting amplifier, the gain of non-inverting op amp, the gain of non-inverting amplifier of an operational amplifier. Now V2 is equal to, so if we consider this equation, we can write a V2 is equal to V naught divided by A naught, V naught divided by A naught. So now at node V1, so at this node we are going to consider, so at v1 what happens at v1, at node v1, at node v1 you can see this, the current entering is i1, and at node v1 the current entering is i1, the current entering here is i1, and i1 is equal to i2 plus i3, because as we have discussed that I1 is coming through V1, V input voltage, and then at this node it is going to divide into two parts. So we can write this I1 is equal to I2 plus I3, because I1 is going to divide into two parts. So we are going to write equation for this I1, I2, and I3 using nodal equations. So that can be written as, I1 can be written as, so Vi input voltage minus V1 divided by the reactance in this path, that is SC. So we are going to write this SC, or we can write as divided by XC also we can write Sc into Vi minus V1, which is equal to I2. So where we are going to consider this I2 here. So the voltage at this node is V1, and the voltage at another node is this V2, V0, and the resistance in this path is R. So V1 minus V0 divided by R. This is what we are going to write in the place of I2. And when we are considering I3, so see here I3 is the current flowing through this capacitor. So here the voltage at this node is V1. So V1 minus the voltage at this node is V2, V2, and the reactance present in this path is SC. So into SC. So SC Vi by Vi minus V1 is equal to V1 minus V0 divided by R plus SC into V1 minus V2. So by solving that equation, so see here in the place of V2, as we have discussed here, V2 is equal to V0 by A0. In the place of V2, we are going to substitute V0 by A0. So that's what we have substituted here, and we are going to assume this equation as equation number 1. And at node V2, if we consider this at node V2, we can say that I3 is equal to I4. I3 is equal to I4, as I have discussed that. Why? Because here we are considering op amp as a ideal op amp. Here we are considering op amp as an ideal op amp, and here the op amp is not going to draw any input current, because The op-amp is not going to draw any current. Hence, we can say that I3 is equal to I4. So that is why we have written here at node V2, I3 is equal to I4. And again, if you write the equation, so I3 we know that V1 minus V2 divided by C, and I4, in the place of I4 we can write that, how we can write this I4? So V2 minus 0, because the voltage at this node will be 0, that is the ground potential is nothing but 0. So V2 minus 0 divided by R, which becomes V2 by R. So that's what we have written here. Sc into V1 minus V2 is equal to V2 by R. So in the place of V2 we are going to write V naught by A naught here, and here in the place of V2 we are going to write V naught by A naught. Why we are going to write this means, so here our aim is to obtain the transfer function. So transfer function means nothing but, so the transfer function means, so V naught by Vi we have to find. So for making the equation, for bringing the equation into V naught by Vi, we are going to replace it with V naught and Vi. In terms of V naught and Vi, we are going to write the equation in terms of V naught and Vi. That is why we are going to write this equation. So by solving this equation, so we are going to get V1 is equal to V naught by A naught plus V naught divided by A naught into SCR. So this is what we are going to get the equation finally. And this is, we are considering this equation as equation number 2. So by substituting this equation number 2, that means as our aim is to bring the equation in the in terms of Vi and V naught, so we are going to replace V1 also with V naught. So for that reason we are going to write, we are going to substitute v1 value in equation 1 in the place of this. So if we see, if we observe now, if we observe this equation, so here vi, and here in terms of v naught it will come like that. So what happens, by substituting this equation, SCVI is equal to 1 by R S2C 1 by A naught, and by solving that we are going to get this equation. So after solving this equation, so SCVI is equal to SCR whole square. So this is what we are going to take a common V naught as a common term, and then we are going to bring this SC to this side, and uh, we are going to bring this whole term to this side, and we are bringing this Vi to this side. So this becomes V naught by Vi, and here if this term will come this side, then A naught into SCR square divided by SCR square plus 3 minus A naught into SER plus 1. So this is what we are going to get the equation. So then this can be written as, so we are going to divide the equation with the RC on numerator and denominator. So then the equation becomes, that is RC square, nothing but, so the equation becomes A naught into S square divided by, here RC square and RC square will be cancelled, and 3 minus A naught, RC, as RC square we are going to divide, so CR will be, RC will be cancelled here, and RC will remain here, and 1 by RC square. So the equation will becomes like this: A naught into S square 3 minus A naught into omega naught into S. So we are going to write this 1 by RC as omega naught, and omega naught square 1 by RC square as omega naught square. So where omega naught, here you can see that omega naught is equal to 1 by CR. Then the damping factor here, this determines the damping factor. So this determines the damping factor. This determines the damping factor. So that is a 3 minus a naught. So alpha is equal to 3 minus a naught, which is the damping factor. So we are going to write the transfer function h of s is equal to a naught s square in divided by s square alpha omega naught into s plus omega naught square. So for a second order high pass filter, the transfer function will be h of s is equal to a naught s square divided by s square plus alpha omega naught into s plus omega naught square. As the damping factor alpha is equal to 3 minus a naught, so as we have observed here, so in the place of a naught we can replace it with its a transfer function. That is here the a naught is nothing but the gain of non-inverting amplifier, so which can be written as 1 plus r1 by r2. So in the place of the gain of uh, in the place of a naught we are going to write this 1 plus r1 by r2, 1 plus r1 by r2. So now the equation becomes alpha is equal to 2 minus r1 by r2. So in the last slides we have described there the damping factor which is equal to 2 minus r1 by r2. So this is how we have obtained the damping factor alpha, that is alpha is equal to 2 minus r1 by r2. So this is how we are going to obtain the transfer function of the second order high pass filter or high pass filter with two poles. And if we increase number of poles, here you can see this is an example for increasing the poles. So here you can see this is one the two pole high pass RC. This is a two pole high pass RC, and this is a two pole high pass RC. We are cascading three two pole high pass RCs, then this becomes a six pole high pass RC circuit. So which provides an attenuation of that is the roll off rate of minus 120 dB per decade. So here the three two pole RC networks are cascaded. The three two pole RC networks are cascaded. And next, we are going to observe active low pass filter. So see here, low pass filter. Simply, we are going to consider a voltage follower here, and we are giving input here also. We are going to consider Opamp as a non-inverting amplifier, and the signal which is given to non-inverting terminal of Opamp through a low pass RC circuit. And as the feedback is directly given, so this is going to act as a unity gain follower, so in which the output is equal to input. For a unity gain follower, the output is equal to input. So here similarly, as we have discussed in high pass network, here also we are going to consider that the resistance is equal to reactance of the capacitor, and finally we are going to obtain the frequency, critical frequency, which is equal to 1 by 2 pi RC. The critical frequency which is equal to 1 by 2 pi RC, which is equal to 1 by 2 pi RC. So FC is equal to 1 by 2 pi RC. Active low pass filter with a single pole. So here we are going to consider op amp as a non-inverting amplifier So the closed loop voltage gain will be 1 plus R1 by R2. So the critical frequency of C is given by 1 by 2 pi RC. So you can observe here the response, that is the low pass filter. It allows only low frequency signals and attenuates the high frequency signals that is above the critical frequency. Next, second order low pass filter, which is also called a Shalansky filter. So here we are going to consider two poles, that is two RC poles. This is also similar to the high pass network which we have considered there. And here the frequency, the critical frequency is obtained by 1 by 2 pi root of RA plus RB into CA plus CB. So finally, the critical frequency can be determined with the help of 1 by 2 pi RC. Now, if you observe, so up to this, we will stop in this class and we will discuss this active low pass filter in the next class. Thank you, students. Thank you for your attention.